Okay, in this lecture today we're going to continue to analyse the current flow during the transient period, which is the initial period when the first circuit is first turned on before it settles down to a steady state, when we put a step or a ramp potential difference across a circuit containing an inductor or a capacitor. Next time, in the next lecture, we're going to look at investigating this transient period when an inductor and a capacitor occur in a circuit, where it's a little bit more involved. But for now, we're going to focus on putting resistors with capacitors or inductors across ramp or step supplies. Before we do that, let's just quickly review last time. Remember what we were doing? We were analysing networks and finding out what the total impedance of the network was in S space. So this, in other words, this total impedance in S space. Remember when we transform them into each of the components into its S space, into its S equivalent, using the table on page 5. We then treat each of the components, whether they be resistors, capacitors or inductances, just as impedances, so we can use the normal rules for these impedances in series or parallel to combine them. In other words, if they're in parallel, product over sum, and so on. So we went through the algebra around simplifying a circuit like that, and the algebra around simplifying a circuit like this. Noticing here that at this point in the algebra, if I want to combine those two, I can only add if the denominators are the same. So in the 4, I multiply top and bottom by S plus 0.05 so that I can have a common denominator, and then I can combine them and end up with a result at the end. That's a common thing to do, to multiply top and bottom by the denominator of the other fraction so that they're the same. We analyze the flow of current in a network using Laplace transforms and Ohm's law. There's Ohm's law, thinking that V over R as actually E over Z, where Z is the impedance, the total impedance of the network, and E is the voltage we've got across the top. Remember, we're going to limit ourselves to, and we were talking about this last week, to 2 voltage types: the step, which transforms to E over S, and the ramp, which transforms to E over S squared. And last time we looked at a step voltage across a resistor with a capacitor and went through the algebra around that. So let's just, well, that's what we're doing today, is to carry on from there. So let's just quickly review this one and then look at the other examples. So what's the first step? Find the total impedance, ZS, by just adding a 10 and 1 over 5S in series. The voltage is a step voltage of 10 volts, so that transforms to 10 over S, using the table again on page 5. So then Ohm's law equals E over Z. So that's 10 over S over 10 plus 5S, 1 over 5S. And then it's a case of just simplifying it. Can you see, remind yourself how we got last week from this form, 10 over S divided by 10 plus 1 over 5S, to this form here, 1 over S plus 0.02. Just remind yourself of those steps. I suggest the first one is to multiply top and bottom by S. See if you can go and finish off the rest. Once we've got the current in this form, 1 over S plus 0.02 in S space, in other words, like this, we then need to transform back to time as our variable. So we need to use the table on page 5 again, but now in reverse. If you look down the right-hand column, you can see that this particular one is of the form A over S plus B, and that transforms to A e to the minus bt. So in this particular case, b is 0.02 and a is 1, so it becomes e to the minus 0.02t. In other words, what happens to the current in this circuit? If we were to plot this on autograph, we would get the following. So in autograph, we have to enter the equation, and we're going to type in, remember, using y and x as the variables rather than I and t. So y equals e to the power, using the hat symbol above the 6 brackets, minus 0.02 x, close brackets, and then we will get the function plotted. To get it to look sensible, obviously we need to now zoom out on the x-axis because it's stretched out over far too big a period of time. So let's just zoom in on the x-axis and we start to see what the curve looks like. I can zoom in on, just by putting a zoom box in, I can zoom in on part of the circuit. I'm interested in that part. I can maybe zoom out on the y-axis, zoom in on the y-axis rather, to see it, drag it around, zoom in again on the y-axis, drag it down, because we're only interested in what happens after t equals 0. And there is the function, and we can see that the current is decaying to 0, which you would expect, because if you think back to the circuit we had here, it's a capacitor in the circuit. So the instant you turn it on, the capacitor is going to start to charge up, and the steady state is that no current's flowing, because once the capacitor is fully charged, there will be no current. And if we look at the curve, there it is. So this particular circuit, putting this into the notes, this curve, we can use. The current varies with time, measured in seconds, with the relation e to the minus 0.02 t. So looking at the curve, we can see that it's going to take about 200 seconds, looking at this point on the curve, before the current dies away to 0. Okay, let's have a look at some more circuits then. So the next one to try and analyze is a step voltage put across a resistor in series with an inductor. And in this particular case, we're going to find that we need to use the method of partial fractions to solve it, which is something that we've looked at. And so we'll have to remind ourselves of this as we go along. So let's see how to progress. So same idea as before. What we do is we find the total impedance for the circuit in S space. So ZS is going to be this 10, the resistance stays as it is, plus 10S, because the inductor, using the table on page 5, just transforms to 10S. The voltage this time, step voltage again, so as before, 10 over S. So we've got the total impedance and the voltage in S space. So now we can find the current in S space, and that equals E over Z, which equals 10 over S over 10 plus 10S. So now it's all about the algebra, about analyzing this. That's what we're going to be doing, analyzing this, using algebra on it to get it to look like the transforms on page 5. So then we can transform back and find the current in time space. So that's the plan. So the first step, I would divide top and bottom, or move the S rather, to the bottom. And so we get IS equals 10 over S times 10 plus 10S. So the S actually just goes underneath. I could now divide top and bottom by 10 to make it a bit more straightforward. So this will equal 1 over s into 10 divided by 10 is 1 plus s. So we have that is equals 1 over s into 1 plus s, because I've divided the top by 10 and both terms in the bottom by 10. Now, this does not look like one of the transforms in the table. What we need to do is split this fraction, and this is where the partial fractions comes in. So let's just consider this for a moment. 1 over s into 1 plus s equals, using partial fractions, I can split this into some constant over s plus some constant over 1 plus s. I'll split the denominator on the left-hand side here into its two parts. And that means there's some constant on the top and some constant on the bottom. We need to find out what they are. If you remember the process here, what we do now is we effectively multiply a by 1 plus s. So we multiply this fraction, top and bottom, by 1 plus s. And then we multiply this fraction by s, top and bottom. So that the denominator is the same. We can combine them and say that 1 over s 1 plus s equals a 1 plus s plus bs all over s 1 plus s. What's happened there is, on the right hand side, I've tried to make the denominator of both the terms on the right hand side the same as the denominator on the left. So what have I got to do to the first fraction here? I've got to multiply top and bottom by 1 plus s to get it to be the same as the denominator here, s times 1 plus s. If I multiply the bottom by 1 plus s, I've got to multiply the top by 1 plus s, and I get this. Similarly, to get the right-hand fraction the same, I've got to multiply top and bottom by s to get the term on the right here. So now both of these terms on the right have the same denominator, so I can combine them. And this is exactly the same method. This is the method of partial fractions that we always use. So now we equate numerators, if you remember. Equate numerators. An engineer might well not bother to write that step down, but mathematically that's what we're doing. We're saying that if the denominators are equivalent, the numerators must be equivalent. So we can say that 1 equals a 1 plus s plus bs. Okay, so now multiply out the brackets. 1 equals a plus as plus bs. Now collect together on the right hand side terms involving s, factorise for s. So that's a plus s into a plus b. So I can take an s outside the bracket in these second two terms here that involve s. I can take an s outside the bracket, leaving a plus b inside the bracket. Now what we do is we say, and effectively it's as though I've got on the left hand side here, no s's, 0 s's plus number 1. And because we're equating these two, the left and right have got to be the same. In other words, the numbers must be the same. So a equals 1. And the coefficients of s must be the same. This is the coefficient of s, a plus b. That must equal the coefficient of s on the left-hand side, which is 0. So I can write that a equals 1 and a plus b equals 0. So if A equals 1, 1 plus B equals 0. So therefore, B must equal minus 1. So I know B equals minus 1 and A equals 1, and I can plug them back into the original function, which was 1 over S1 plus S equals A over S plus B over 1 plus S, where we split it. Now we know what A and B is. So we can write that 1 over S, 1 plus S equals A, which is 1 over S, and minus, because B is minus 1, over 1 plus S. And now, each of these in turn can be transformed. If you look at the table on the right, we can write down now what the transforms are. So IT, going back to time, space, is going to be given by, if we look at 1 over S, that's just 1, that's the top one in the table. And then the other one is just like the fourth one down, is it? Yeah, which we had before. So this is going to equal minus e to the minus t. So if we plug this into autograph, you can see that everything's going on right at the beginning of this period of time here. So let's zoom in on the x-axis to spread this out a bit, and we start to see what the function looks like. Let's move it along because we're only interested in what happens after t equals 0. So if we look at this now and compare that with the circuit we were looking at, which was going back an inductor, if you think about what's going to happen, the instant I turn the circuit on, there's going to be a back EMF which is going to add to the resistance of the circuit, but effectively that's going to die away as time goes by. So the current will start very low and build to a maximum value when the inductance has effectively disappeared. And so you would expect it to look like that, the current starting at 0 and then building up to a steady value of 1 amp in this case. And if we look at the original circuit, we've got a voltage of 10 volts and a resistance of 10 ohms. So eventually, once the inductance has disappeared, the current will be 10 divided by 10, which is 1 amp, which is exactly what we have here. More than that, we can usefully tell from this circuit, if we look at it, that it's going to take around about 5 seconds here for the current to reach its steady state, which is its use. That's the transient period. How long does it take before this circuit settles down to its steady state? About 5 seconds. Okay, so now let's have a look at these. You try these two circuits. 20 volts DC step voltage. You see 2 ohms and a 4 Henry inductor, and a 6 volt DC step voltage of course capacitor of 1 power and a resistance of 2 ohms. You might find it easy to do number 2 before you do number 1. Don't forget, if you're going to do the transform, that don't forget, if you're going to do the transform, that S must be 1S. So in other words, looking at number 1, you should get the solution when you use partial fractions that I in S space equals 10 over S minus 20 over 1 plus 2S. But of course, to make the transform, S must be just one lot of S. So therefore, I need to, in the second fraction, divide top and bottom by 2 to get the solution below, and then transform it to get the value for I. Again, number 2, you should get that solution for the I in S space, and then that transforms to 3 e to the minus 0.5t. When you've had a go at those, look at the textbook, the notes that you got on the Laplace transforms, transient analysis. Turn to page 21 and have a go at questions number 1 and 2. And then when you've done that, go to the next video, which looks at the next circuit.